Next we have number 6, where we have to show that there are infinitely many integers n, positive integers of course, for which phi of n is a perfect square. So in the solution we considered these integers n 2 to the power 2k plus 1, where k is a positive integer. So as you change k, you get different values of n. So that's how you are getting infinitely many integers. And for any such n, if you calculate phi of n, then as you already know that if the number is a power of 2, then you have to divide by 2. You have to divide the number by 2, that will be its phi value. So ultimately you are getting this 2 to the power 2k, which is a perfect square. So that's how you have infinitely many integers whose phi values are all perfect squares. Next we have number 8, where we have to prove that if the integer n has r distinct odd primes, then 2 to the power r divides the phi value of n. The solution starts with this simple case that the result is trivial if n is equal to 1. If your number itself is 1, then it's not divisible by any odd prime, or in fact by any prime. So in this case r is 0. But then 2 to the power r is 1, which obviously divides phi of n. Also, the result anyway is trivial if r is equal to 0, regardless of what n is, irrespective of n. And that is why we can now assume that n is greater than 1 and r is positive. R is greater than or equal to 1. Now because n is greater than 1 by the fundamental theorem of arithmetic, it will have a prime factorization. And taking everything into account, the prime factorization will have this form, where k0, the exponent of 2, is non-negative. You have to keep the possibility alive here that actually n may not be even. N may be odd, n may be even. So if k0 is 0, then n is odd, otherwise n is even. Okay. And along with that we have these prime powers, where all these primes are distinct odd primes. R number of them are there, and their exponents are all positive, because it's given that n is divisible by r distinct odd primes. That's why. Now if k0 is 0, if the exponent of 2 is 0, that means n is odd. Let's calculate phi of n in that case. So n now looks like this, no 2. So you know the phi formula, the integer comes and gets multiplied with these things. 1 minus 1 divided by a prime factor of the integer. So just like that all the prime factors come. But then when you take these p's outside, then you get these other factors, and those p's divide the respective powers, their own powers. And these powers can take the blow of being divided because these exponents are positive integers. So these exponents now are non-negative integers. Okay, they are not negative. So we are not getting any fraction. And along with that we have this. So that means because these exponents are non-negative, so this part is an integer. So that's why this product divides phi of n. We are going to note this. And next we are going to see the other case where n is even. And if k0 is positive, that is when n is even, the only change in the calculation is here. So for that, power of 2, an extra 1 minus 1 divided by 2 comes, which is just 1 divided by 2. So that makes this power the next means the previous lower power, 2 to the power k0 minus 1. The rest is same. And in this case also, this product divides phi of n. And that is our main observation. Now the point here is that each such pi is an odd prime. So each such pi minus 1 will be divisible by 2 because that will be even. So each one of these factors in this product will be divisible by 2. How many factors are there? R. So that's how 2 to the power r divides phi of n. That's what we wanted to prove.